Okay, so in this section, we want to begin to take a look at propositional logic. This will help us as we progress through primarily the next section when we introduce the idea of proving mathematical concepts. But first, let's define what's called the conditional proposition. So let P and Q be propositions. The proposition, if P then Q, is called the conditional proposition, and it is denoted by P and then this arrow Q. And this is literally read, if P, then Q. Now, these two statements that we have right here, or these two propositions, P is called the hypothesis, or sometimes we might call it the premise, or in a philosophical setting, you might call it the antecedent. The proposition Q is called the conclusion, or in a philosophy class, you might call it the consequent. Primarily, we're going to stick to the word hypothesis for P and conclusion for Q, or we might use the premise as well for the first proposition P. But the idea is we read this if P, then Q, or P implies Q. So, very, very basic example. Let's let P be the proposition, I wash the dishes. Now, that's true, or it could be false. Okay, I could come home today. I could wash the dishes. That could be a true statement, or I could get really busy, or I could be lazy and I choose to not wash the dishes. So P is the statement or the proposition, I wash the dishes. Q is the proposition, my wife will be happy. And so the proposition P, if P then Q, is simply read as if I wash the dishes, then my wife will be happy. So this hypothesis is the if clause stating I wash the dishes. The conclusion is the then piece, my wife will be happy. Now, just like we had just like we have truth tables for conjunctions and disjunctions, we also have a truth table for the conditional. So this is the truth table for the conditional if P, remember this is read if P, then Q. So if I look at this truth table, I notice that the conditional proposition if P then Q is only false when Q is false, and it is true otherwise. So the statement is false only when Q is false, and it is true in each of these other three instances. So let's discuss what we would call a converse. Let's let P, Q be propositions, and P implies Q be a conditional proposition. So if P, then Q. The proposition Q implies P is called the converse of P implies Q. So the converse Q implies P is simply read if Q, then P. So let's take a look at an example. Let's let P be the statement, John visits the Statue of Liberty, and Q be the statement, John visits New York City. So I simply want to note that P implies Q is true. So simply say, if John visits the Statue of Liberty, then John visits New York City. Simply meaning, if he's in the Statue of Liberty, then he's also in New York City. However, Q implies P, or the converse is false. So, meaning just because John visits New York City does not imply that he visits the Statue of Liberty. There's lots of other places that I could go and visit in New York City other than the Statue of Liberty. So this is a very important thing to notice, that just because P implies Q is true does not imply Q implies P is also true. This is a very common mistake that elementary mathematicians and computer science students make, is that they incorrectly assume that the converse is true. Just because the conditional, this P implies Q, is the conditional, just because the conditional may be true does not mean that the converse also is true. So let us now construct a table for this proposition. Okay. So this is read. If I wish to write this in words, this is read: if P, then Q, and if Q, then P. So if P, then Q, that's this clause right here, and if Q, then P. So if I begin to construct my truth table, so P and Q could both be true. I could have a true and a false. I could have a false and a true, or a false and a false. So the conditional, P implies Q, is true, false, true, true. And Q implies P is true, true, false, true. Now, let us begin to set up the and of these two statements. My first statement, I guess you could simply call it 1, and here's my second statement 2, is if P, then Q. So if P, then Q, and it's imperative that we look at this connector right here, and if Q, then P. So if both of these are true, then the connector and is also true. However, if one is false and the other is true, then the and is false. If one is true and the other is false, then the and is also false. And if both of them are true, then the and is true. Okay? It might be good to recall. It might be good to recall for any statements P and Q, okay, that it's true only when both statements P and Q are true. So because in, I guess I could call this case 3 and case 4 right here, because I had a false in one of these, then the end result was false. So this leads us to a new definition, which we will call the biconditional statement. Okay? So let me erase this right here. So the statement, if P then Q and if Q then P, is called the biconditional statement, and it is notated P with this double arrow Q, and it is read P if and only if Q. So if I were to construct this truth table quickly, and this column right here is going to be what was in this last column in this previous example. True, false, false, true, false, false. So what was it in the previous example? It was true, false, false, and true. And so notice that P, if and only if Q, is true only if P and Q are both true, or if P and Q are both false. So this is a very important thing to notice. And we call this the biconditional, this double arrow right here, that my end result is true only if P and Q are both true, or if P and Q are both false. So let us consider the following propositions, and I simply want to write them out in English. So P is the statement, a natural number that ends in 0. So what would P look like? A natural number that ends in 0, so 10, 20, 30, etc. And Q is a natural number that is divisible by 5. Well, if it's divisible by 5, then that means it ends in 5 or 0, so etc. So let's take a look at this first conditional statement. If P, then Q. So if a natural number ends in 0, then what's statement Q? The number is divisible by 5. Let's look at the second one. If Q, then P. So this would be read, if a natural number is divisible by 5, then the number ends in 0. And lastly, P, if and only if Q. This would be a natural number ends in 0 if and only if, that's what the double arrow means, okay, the number is divisible by 5. Now, what am I simply doing with this example right here? I'm practicing converting these statements into words. I'm not saying that any of these conditional statements are true or false. Okay, I would leave it to you to actually think it through and see if any of these three are true or false. But we are simply practicing writing them out in English. Okay? We're going to skip this next one and take a look at this example. So let's let proposition P, Sam had pizza last night. And I don't know if that's true or not, okay? It is true or it is false, and that's true for me or for you as well, okay? Last night, I either had pizza or I did not, okay? But we're going to make the proposition be that Sam had pizza last night. Q, Chris finished her homework. And R, Pat watched the news this morning. We may not know the truthfulness of these statements, P, Q, and R, but each of them are either true or they are false. Either Sam had pizza last night or he did not. Either Chris finished her homework last night or she did not. And Pat either watched the news this morning or he did not. So what I wish to do is to write a symbolic statement for each of the following. So Sam had pizza last night if and only if Chris finished her homework. So this would simply be P if and only if Q. Pat watched the news this morning if and only if Sam did not have pizza last night. So we would say R if and only if Sam did not have pizza last night. So that would be not P. Thirdly, Pat watched the news this morning if and only if, so this would be R, if and only if Chris finished her homework and Sam did not have pizza last night. So how would I write this? And I'm going to need to incorporate the parentheses right here. This would be Q and not P. If and only if Chris finished her homework, Q, and Sam did not have pizza, that would be not P. Okay, lastly, Chris finished her homework if and only if, so Q, if and only if Sam had pizza last night and Pat did not watch the morning news. So this would be P and not R. So this helps us begin to see how we would make symbols and these logical connectors out of these statements in English. Okay? Now, let's take a look at a definition. Suppose propositions P and Q are made up of propositions P1 through Pn. We say that P, Q are logically equivalent provided that given any truth values, P1 to Pn, either P and Q are both true or P and Q are both false. So let's fill this example in. Consider a truth table for this proposition. Okay? So if I fill this in, so true, 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 false, false, true, false, false. Okay. So P or Q. So true, 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 false. If I negate P or Q, so I'm going to take this previous column right here and I'm going to negate all of them. So that would be false, 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 and true. Okay. So in essence, I did this one first, I did this one second. I'm going to do this one third, and then we'll do the connector, the if and only if, last. So not P and not Q. So not P and not Q would be false, 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 true. And now I'm going to use the biconditional definition to find out each of these. So false, if and only if false, well, that's true. False, if and only if false, that is true. False, if and only if false, is true. And true, if and only if true, is also true. Okay? So notice that not P or Q, that's what this is saying right here, not P or Q is logically equivalent to saying not P and not Q. And so we simply say P is logically equivalent to Q, where this right here is what I'm calling P, and this right here is what I'm calling Q. Okay? And if we think about it, it makes sense. Okay? Not P or Q is logically equivalent to saying not P and not Q. Now, notice, okay, that this is true always, and so we would say that this is a tautology. This column right here, this biconditional connector, is always true, and so we have what is called a tautology. Okay? Now, this shouldn't come as a shocker if we remember De Morgan's laws for sets. Okay? This one right here says A or B complement. What is this saying? This is saying not A or B is equivalent to not A and not B. Well, that's exactly what we just saw with this previous example, simply using P's and Q's. Okay, let's take a look at this next truth table. So let's construct a truth table for this statement. So true, 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 false, false, true, false, false. Okay. So here is my first proposition, which I would simply call capital P. And here's my second one, which I would call capital Q. Okay, so let's fill in this right here. So let's do P and Q negation. So if I do P and Q and then negate that, I would get false, true, true, true. Now, so we did that one first, we'll do this one second, and then third we'll look at the biconditional connector. Okay? Not P or not Q. Okay, so not P or not Q would give false, true, true, true. Now, lastly, let's look at the connector. Okay? If I have a false, if and only if false, well, that's true. True, if and only if true, is true. True, if and only if true, is true. And true, if and only if true, is true. And so I notice, okay, that P, and this is not P and Q, is logically equivalent to not P or not Q. And so we write P is logically equivalent to Q, and this should be very similar to our other law of sets, our other De Morgan's law that we looked at in a previous section. Now, let's take a look at something called the contrapositive. The contrapositive of the conditional statement, if P then Q, is the proposition, if not Q, then not P. Okay? So let's take a look at this example. Consider the conditional statement below. If there's a bug in the program, then the program will not compile. So the P is there is a bug in the program. The Q is the program will not compile. So if P, then Q. So Q and P. Now, let's take a look at the contrapositive. Okay? Not Q implies not P. So what would this be? This would be if the program will, and this is poor grammar, but I'll write it, not compile, then there is not a bug in the program. Now, this whole not, is poor English, and it's the whole idea of negating a negation turns it into an affirmative. And so if the program will compile, then there is not a bug in the program. And hopefully we would see that this is logically equivalent to the statement if P then Q. For you computer scientists out there, if there is a bug in the program, then the program will not compile. That is logically equivalent to saying if the program will compile, then there is not a bug in the program. So, we're going to skip this next example, but I do want to at least emphasize this theorem. No, I do need to do this theorem and this proof because it is relatively important. So the conditional proposition, if P then Q, and its contrapositive, not Q, implies not P, are logically equivalent. Okay? So let's do a very brief, quick proof for this one. Okay? So P could be true, 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 false, or false, true, false, false. Okay. So P implies Q. This would be true, false, true, true. Okay. Not Q would be false, true, false, true. Not P would be false, false, true, true. Now, if I do not Q implies not P, this would give me true, false, true, true. Now, I want to compare, or I want to show that P implies Q is logically equivalent to not Q implies not P. The idea is that this right here is P implies Q. This column right here is not Q implies not P. Notice that these are the same, okay? True, false, true, 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 false, true, true. Okay? These are the same for all P and Q. So P implies Q is logically equivalent to not Q implies not P.